All right, here's the question. The radioactive isotope of lead, 209, decays at a rate. It falls apart at a rate proportional to the amount present at time t and has a half-life of 3.3 hours. If 1 gram of lead is present initially, how long will it take for 90% of the lead to decay? So they're giving you a rate. That means you need to be setting up a differential equation. So here's the rate. So it decays at a rate. So you have a change in the amount during a change in time is the rate of decay. They're saying that that's proportional. We're just going to go right to equal. We're going to use the constant of proportionality k, but it's negative because it's decay. It's leaving the sample. The sample is getting smaller. It's not growing. It's shrinking. So that's for the negative. And then it's proportional to also to the amount that is there. The more that's there, the higher the rate is going to be of decay. The more there's there. You know, they're also telling us the half-life. The half-life is the amount of time until 1/2 of that product is gone. So you think of a bunch of uranium that's decaying into lead or something like that. Then after when half of it's gone, the time it takes for half of that to go away, that's the half-life. And that's going to be the same for the next half. And the next half, it's a constant half-life. All right, so here's your differential equation. So I'm going to solve this. Last time I talked about you could solve this 2 ways. Find the integrating factor, separate the variables. It's way easier to separate the variables, so I'm just going to do that. So I'm going to bring the dt up here and the a down here. So we're going to have 1 over a dA equal to negative k dt. See what I did? Take the integral of both sides. What do we got here? Log a equals negative k t. Okay, just basic integral. Now we're going to get rid of log because we want a. So we're going to put that over the e. Then we're going to put the e right here. Oh, there's a constant of integration. We forgot that. That's right there. Okay. So this inverse functions cancel out. We have a equals e to the negative kt times e to the c. E to the c is just a constant. So we have a equals c e to the negative kt. That's our first part. That's our equation. That's the equation we're gonna need to use, which is just the solution to this differential equation. This is just the solution to this differential equation. We were able to set this differential equation up by what it says right here in the beginning. Once you set this up, take t at 0, and that's going to give you your c. So a at 0 is equal to c times c, because if you let t equal 0, it takes care of all of this junk right here, because it's all at 0, to negative k times 0. Anything times 0 is 0, so that's just 0. This becomes 1. So we have AO equals C. So now instead of C, use AO, and we rewrite it. A as a function of time equals AO, which used to be C, e to the negative k over t. Now we need to find k. So this is our second big step we've made here. We found C. C is equal to AO. Now we need to find k. Well, what do we know? We know that when t equals 3.3 hours, there will be 1/2 A, the original amount, AO, left. So AT will equal 1/2 AO. Okay, so then let's put that in. We got AT equals this, so we say 1/2 AO for AT. A is a function of t equals AO e to the negative k t. These AO's go away, you divide out the AO, we have 1/2. So let's take the log, natural log of 1/2, equals the natural log of this. We'll just bring it down like this, right? So we have the natural log 1/2 divided by t is 3.3. We didn't plug that in, but t is 3.3. See, it says right here, t is 3.3 equals k, which equals what? I don't have my calculator. Hold on one second. One second. All right, here we go. So, turn the sucker on. We got natural log 0.5 divided by 3.3 equals, this is negative actually, see, negative. I need to put the negative down there to make this positive. 0.21. So, now we've got the whole thing. We've got A given T equals AO, that used to be our C, times E to the negative K, which is 0.21 times T. This is the most perfect equation. This is what we wanted. We wanted the amount as a function of AT. So now we can go right to the question here. We have 1 gram of lead present immediately. So AO equals 1 gram, right there. How long will it take for 90% of the lead to decay? So we're solving for T. We want to know what T is. So if 90% of the lead decays, that means that there will be 0.10 times the original amount, which is just 1. So 0.10 times 1, the original amount, that's how much will be left, equals AO, which would be 1 e to the negative 0.21 t. We're solving for time now. So this would be 0.10 equals e to the negative 0.21 t. Now take log both sides. We got log 0.10 equals negative 0.21 t. Log 0.10 over negative 0.21 equals t equals, and then that's going to equal natural log 0.1 divided by negative 0.21 equals 10.96 years, or just 11 years is fine.